Hi, welcome to my channel JaberTime. Another problem about the kernel. I'm a little bit focused on the kernel because it covers a lot actually. It helps understand the bases, the kernel, the range, the dimensions, the graphs, and even more. This problem here, it says consider the linear transformation from P2 to P2 defined as follows, where A and B and C are arbitrary constants, scalars. We need to show that the kernel is consists of all polynomials of the form b multiplied by x minus 2, and hence find the dimension, find the range and its dimension. Let's get started. Here's the problem again, and now we need to slow down and show the kernel. Well, the kernel by definition is when you have vectors in P2 such that the outputs, that's the output, how they look like, is equal to 0 for all x. But for this to happen, for P of x to be in kernel, everything has to be zeros in terms of A and B and C. They must satisfy the system, the following system. We have A equals 0. We have A plus 2B plus C combined, not A as I mentioned and B and C individually equal to 0. So this component will be 0. This right here will be 0. And this here will be right 0. But since A is 0, the second equation and the third equation will reduce to the following. We could eliminate the A's in it. That's what I mean. But notice that the third equation is identical to the second equation. Like if you multiply by -1, that's what you have. So let's eliminate that too. By eliminating that and putting C by itself, we're going to say C equals minus 2B. Alright, now let's enhance that even further and tell you what's happening with the kernel. So we have A equals 0, we have B equals B, and we have C depends on B. So by knowing B, C is minus 2B. Okay. Now, the main focus is the kernel. We need this to happen. By doing some algebra on the side, this is what I came up with. All polynomials of the form ax squared, that means 0x squared. We kept b as b right here, and that's bx minus 2b are in kernel of t because of the following. We have b equals b, we just say that here, and the c part right there is minus 2b. That's how the polynomials in the kernel will look like because of the condition that we started right here. So the kernel of t will be just bx minus 2b. We don't have to mention the first part, as you could see. Differently, I could take b out as a common factor from these two terms. See, the b is underlined. And now I have b times x minus 2. Well, remember in the problem, it mentioned that. So let me take you to the problem. The problem says, show that the kernel of t consists of all polynomials of the form b multiplied by x minus 2, and hence find its dimension. Let's go back. So we got this part. So how do you identify the dimension? Well, it is simple once you get used to it. It's just one vector, x minus 2, and we have scalar multiplications of one vector. Since the kernel of T is spanned by the non-zero vector x minus 2, it follows that the dimension of the kernel is just 1. As I said, it is simple, but it's a new language. If you're not used to it, it will slow you down and you might start wondering what's the dimension. The dimension is how many linearly independent vectors in the basis of the kernel in this case. Let's look at the range. Well, the range will be the outputs, okay, in W. But how do they look like if you go in detail? Well, that's generic. This is how they look like, because it's defined, the transformation is defined this way. But that is not clear. I need to see the linearly independent vectors, and the best way to see it is when you look at scalar multiplications, linearly independent. So, I'm using colors. For A, I'm going to use red. For B, I'm going to use green. And for C, I'll use blue. I don't know if you could see the blue, but it is blue, it's not black. Simplifying, using distributive property right here. A times x and 2b times x and c times x, and combining everything alike. This is what I mean. We're going to put the b's together. We're going to put the c's together. Everything has a c in it. The last two terms will be right there. That's c times x minus 1. The b is right there. We're going to take b out from these two terms. We'll have 2x in the front minus 2 next to it. All these three terms, one came from the first, one came from here, multiplying a times x, and one came from 3a by itself on the last part. That's what I have for a. Take a out as a common factor, and I have this. You could see probably clearly that we are looking at linearly independent vectors and a linear combination. But before we go and get excited and jump to the conclusion that it looks like we have three vectors, but not really. The second vector and the third vector are identical. If you notice 2x minus 2 right here and x minus 1, they are somehow similar. What do I mean by this? Let's take this 2 out as a common factor. So we'll pull the 2 next to the b outside. So this vector is now x minus 1, identical to this vector x minus 1. So those two vectors are identical, which means I could combine them, and that will end up 2b plus c multiplied by x minus 1. B is a scalar, c is a scalar, 2b minus c is a third scalar. Let's call it d, but this time use a thick marker. So that's what I have. So d is 2b plus c. I did not write it down here. I figured, like, we could just agree on it and move on. So we do have the scalars a and d. We have two independent, linearly independent vectors. So, since the vectors in this spanning set are linearly independent, you can tell that they are linearly independent. They are not scalar multipliers or multiplications. There is no linearly independent means I can't get one of them by multiplying the other one by a scalar. Linearly independent. Earlier, these two are not linearly independent because if you multiply this by 2, you get this. So, are linearly independent on any interval? It follows that the spanning set is a basis for range of t. So, the range of t will be the span of these two linearly independent vectors, meaning the dimension is only 2. I say only, it could be like more, but I don't know why I said only. 2. Okay, let's now go back and visit the General Rank-Nullity Theorem. The General Rank-Nullity Theorem says if we have a transformation from V to W that is defined as linear transformation, and V is a finite dimensional, then the dimension of the kernel plus the dimension of the range will be equal to the dimension of V. For the dimension of P of n, it's going to be n plus 1. For P2, we need to have a sub 0 plus a sub 1x plus a sub 2x to the second. So we do have the scalars a sub 0 and a1 and a2. So what are the bases? The bases are p sub 0, p sub 1, and p sub 2. And that's a 1, and that's an x, that's an x squared. So to build a polynomial in second degree, you need these three vectors, multiply them by scalars, different scalars, doesn't have to be the same, add them up, and you'll get whatever you want. Any polynomial of second degree will be generated from these three bases or vectors in the bases. So what's the dimension of V? V was P2. It's going to be 3. 2 plus 1 would be 3. And we could see why we said 3. Now, we are dealing with P2 to P2. That's my V, that's my W, and V is P2. Dimension of V is, we said, 3. Dimension of the kernel was 1, since we had one vector. Do you remember when I took you back to the problem and showed you that it's b times x minus 1? And the range was 2, which is 2 linearly independent vectors. The dimension of V, we said it's dimension of P2, which is 3. And now we have kernel dimension plus dimension of range equals dimension of V. To double check to see if it verifies, we have 1 for the kernel, 2 for the range, 3 for V, and 1 plus 2 equals 3, and that should do it. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.